Okay, so we are going to start talking about this thing Scala has, which is implicits. We'll start making a mistake here. We have not implicits. Implicits is an adjective, not a noun, so you can have implicits in plural. So it's implicit values or things. It's something implicit you have in your program. We'll start in the presentation, we'll start with easy concepts, just like moving your pieces in chess, but with implicit techniques. In order to reach a better level of knowledge as the slides goes. So first of all, I'd like to start with a Scala 101 class in order to not, because I believe that you know these concepts, just to use the same vocabulary, okay? The first thing I want to have clear here is that what are formal versus actual parameters. Okay? You define a function, you have formal parameters, and these formal parameters are just the names you have of the values you receive in the function when it is called. But that's the name you give to them and their type. On the other hand, you have the actual parameters, which are the actual values you are passing when you are invoking it. I will use formal and actual parameter distinction over the next slides, so keep that in mind. We have values, okay? And values is just a variable, reference to some value, which isn't going to mutate. Okay, the next thing is the next basic concept that we have to keep in mind is that we have in Scala, in contrast to C++ or Java or other programming languages, is that we can have several lists of parameters in our methods, just in our methods, okay? That means that this method here, I don't know if you see it clearly. Okay, you have method f with 3 parameters, but x and y are in the first parameter list, whereas z is in the last one. Okay, this is obviously the return value. As you can see here, we have another example receiving a list in the first parameter list and a value in the second. This, at the end of the day, this gets translated into the JVM bytecode as regular methods, okay? We don't have this concept in the JVM. So if you try to make overriding in your objects, you just make a distinction in how your parameters are distributed in the parameter list, it won't work. Because at the end of the day, the bytecode will interpret it as a single parameter list, and you will find a collision there. And that's quite a tricky problem. Methods, one important distinction we usually don't have in mind is that methods aren't functions, okay? Many people tend to confuse these terms, and they are not the same at all. You have a method, which is a kind of function within an object, and you define with def, you put the list of parameters and the return value. Okay, it's like a property, an attribute of that class or object. On the other hand, functions are values, and they are not part of an object. They are a first-class citizen. You can, for example, one of the distinctions you have to keep in mind is that you can have functions with multiple parameter lists. Functions are just something going from a type to another. You can have several actual parameters, but you can have implicit parameter list. We'll see what's that in a few slides. You're limited in some ways, and you can pass them as they were parameters to other methods or functions. But you may be thinking, okay, I have already passed methods to other functions in a higher order way. Okay, what the compiler does is cheating. It is cheating. It is making a conversion between the method and a function. So whenever you try to pass a method identifier as if it were a function, the compiler will make that conversion for you. That's important to keep in mind. So we'll start with the real contents of the talk. Let's know our implicit things. The first thing, implicit thing we have available are the values. Okay, I just forgot. Yes, it's implicit parameters. Okay, you can define a method with a special parameter list, which is usually the last one, which is able to receive an implicit parameter. Okay, imagine you have this simple method, which is f, receiving an integer and returning a string. And if you are working with your core and you try to call this method just without passing any actual parameter, you will get obviously an error because you are not passing anything to it. Okay, obviously it doesn't know how to continue. The compiler struggles because it doesn't know how to continue. Okay, I heard once that there is something called implicit things. Let's try putting an implicit there. Let's see if that helps to solve the problem. What do you think is going to happen? Just like this. There isn't anything else in the code, just this. Okay, it'll fail because obviously you are not passing anything to it, and you haven't defined what an implicit value available to the compiler to use when this is called with the parameters. But this is the cool thing. You can have an implicit context with things for the compiler to use. These things are selected just by their type. Okay, so we have a certain point in our code. We have this value 42 with this short name, as you can see. You have this definition for the method f. If you call f without anything, it will receive this value. Why? Because in the implicit context, we have a value of type integer labeled as implicit. So the compiler knows how to continue. It's a kind of helper. It's a kind of a resource set for the compiler to continue when it's struggling to compile your code. There is another implicit thing. Okay, we have already visited what are implicit parameters, but there is another thing. This thing is implicit conversions. Let's think about what is a conversion. A conversion isn't more than a function, because a conversion is, let's think, what's a conversion? It's something that you are applying to a value to get another value. That's all. That's the same as having a domain and traveling to a codomain. Okay? Yes, in this case, we have the domain of per, which is double, and we have numbers, and we have a function going from double to this instance of this type, speed. It has two attributes, value, which is double, and unit, string. For example, you want to represent speed, and then you will put in unit meters per second. So you can write a function to go from your double values you are receiving from sensors or IoT application or whatever, and write the function like this, from double to speed. And you build a function, you build an instance of that class. Just you calling its constructor and giving a default unit for it. Okay, but you can do it differently. You can use an implicit conversion. As you can see, we see always the same thing. A value and a value tagged with an implicit word. That means that when this declaration appears, the compiler knows that it has something available for it when it doesn't know how to continue. Another way to express this is to express it as a method. And you might be wondering, you told us that implicit are only values. Yes, but with the compiler it's cheating us because it transforms this method into a function, and this becomes the same as the code above. So this type is the type of the function, is the type of the input value, and is the source type. keep this in mind because we will be using this terminology in some slides after this one. And this one is the target. It's obvious why they are called like that, because we are going from the type of the domain error, which is double, to the type speed. Like Lucas Walker, who knows, it has instead an evil father, it has two. Okay. So let's consider this application. You are writing a piece of code for a non-profit organization which is working with databases containing biological information of guinea pigs, because this database is being used to list ingredients for a restaurant, a Peruvian restaurant, okay? And this kind of restaurants serve this kind of food. There's a guinea pig, we consider it's a pet, but they consider it's food. But this organization has put a target. And this target is to save these poor guinea pigs, transform them from food to pets, okay? So it has to handle with two databases and two domains. We have the domain of the food domain. So we have a way of representing guinea pigs, which is as food. As food, they only care about age and weight. That's important parameters here, because we are in the food domain. We don't give anything at all about the guinea pig. We just want its weight and its meat quality given by its age. On the other hand, we have a database of pets. And when you have an animal as a pet, you usually provide it, a name for it, and an owner, which it might be optional because it's in the process of adoption, or you have already an owner and you provide a value for it. So that's why it's optional. The point is that we have two domains, two ways of representing this guinea pig. And we are writing a software aimed to work with these two domains together. It will be a kind of, I don't know, it will be disturbing to have to be transforming the instance of this domain to this one. So why don't we use an implicit conversion to seamlessly work with food as if we're guinea pigs? And that's the goal of this implicit conversion. We receive, I don't know if the code is clear from there, but we define an implicit conversion called food guinea pig to pet, receiving an actual formal parameter of the food domain guinea pig, that is, the type without owner or name, just age and weight. And we return a pet. We return an object of an instance of a class of the domain of pets. So we transform from food to pets. And that's made with some implementation. We give a fake name or an empty name, Yondo pig. We have no owner yet because it hasn't been adopted yet. And we recycle the age and weight data, okay? Because someone trying to adopt it will be happy to know what the age of his pet is. Okay, so we go from food to pets. This is an example of use. We have an ingredient, food domain guinea pig. We are receiving from the database, from the data access object, we are receiving an instance of the ingredient, get rescued guinea pig. We have the ingredient, okay? And then we use it as a rescued guinea pig. So the only thing we have to do after the conversion has applied is to assign it just like that. We don't have to perform any conversion. The compiler, when he finds this piece of code, will say, okay, the type of this value isn't the same that the type that you're trying to assign it to. But the compiler then is struggling, is having quite a debate there. That he knows from the implicit context, the values we have already defined before, that it has available a conversion to apply. He knows that because he knows that there is a function declared implicit receiving a food domain guinea pig and returning a pet. Just because the types fit, and that's a match in the types, it applies the conversion, and it allows us to receive an audible error. So we have quite an advantage here. This is the obvious application of implicit conversion. So this is the basic part of the talk, okay? We're going to review some concepts. It's important to keep in mind that what actual parameters are, what formal parameters are, that only methods can have implicit parameters. You can avoid writing the parameter for a function call. Functions are values. Keeping that in mind, what do you think implicit conversions are? Okay, they are just values. Implicit conversions are values. Methods are not functions. That's important to keep in mind too. So then you might be tempted not to define implicit conversions as method, but you can do it because the compiler has this internal implicit conversion from method to implicit conversion. So it is tricking you. Most important of all, guinea pigs aren't food, okay? That's not my opinion. In your country maybe, but not here. Oops, this is spoiling everything. Okay. We have been talking about the implicit context. What is this thing, implicit context? The place where magic unicorns come. And what are these magic unicorns? There are these advantages we have. We don't have to write conversions. We can call some functions, some methods without having to pass all the actual parameters. We have some advantages here. So that this is great, okay? Why don't we use it continuously and intensively? Well, you have written your serializer and find this kind of error. That monster error, implicit value is defined twice, impossible to resolve implicit conversion, implicit to resolve implicit value. They are horrible. You might have experience in Scala trying to debug code with implicits, and you may think, okay, this implicit thing is something people, Scala crazy people have created to make it more difficult, to make a more complex language. But that isn't true, okay? That's because people usually don't have a clue how the implicit values and conversions are applied or where they do come from. This monster we have seen before is just a backpack. It isn't just, you wouldn't fire a backpack, would you? I mean, that monster is just this. And the only thing this monster is how Scala resolves the implicit conversions of parameter is when the compiler is struggling, it goes to his backpack and check for things to apply. That's all. And once you have in mind what is the content of your backpack, you just you have that peace of mind that you understand what's going on. And that monster is not a monster anymore. That monster disappears because it's just your imagination made a backpack, from a backpack created a monster. So let's see what's the composition of the backpack. Where do implicit conversions of value come from? Mostly from the scope. You know what scope is. It's the same scope as variables, as values. If you understand how to work with values or variables in a Scala, you already know that implicits, you know how are resolved most of the implicit you might find. Okay, if you have defined an implicit value in an object and you import it using the word import in your context, it is in your scope. Okay, and that's as simple as you were importing a variable or a value. Let's see this example about that. Okay, we have a function receiving an implicit value. The only thing it does with it is called println, showing a message. Basically, it's showing what implicit resolution the compiler has performed. Okay, so we start with this scope. In this scope, we have y with the value humans. Forget about the word implicit. Just keep in mind that you have the identifier y of type string. Okay, and you then enter into this nested scope and call f. What do you think it's going to show? You are not passing y to f, but someone can make a guess of what will be the output of this code? Anybody? Yeah? No, it won't fail because that's a good try. Okay, it won't fail because it's an implicit parameter, and the scope here contains is the same scope as the scope of when you call to f is the same scope as this one. It's just a leveling. It won't fail because it will. We have an implicit parameter. The compiler will try to fail. That will be the first option we will have, and then it will check that there is a value in the same scope of that type. So it will show humans. Okay, it will take that value. Then you enter in another scope with keys, with braces. Redefine y, okay, and call f again. What do you think now will be the result? Yeah, exactly. It isn't difficult at all. If you know how to understand how variables work, you know that having this implicit thing is just a way of being slack and not having to write the identifier over and over again. And there is a third call. This one is interesting. Okay, we define dolphins within this scope, just this scope, and then we are getting out of it and calling f again. Remember, this call to f is in the same scope than the definition of y. So what will we do with now? Obviously, humans. It's as a sandwich of dolphins and humans. Okay. Yes, it's a sandwich, isn't it? And that's the same with the scopes. So we have this. We have already understood what is the biggest pocket in our backpack. Now it's time to analyze the smaller ones, and these are maybe more interesting, even more interesting. Can you believe it? So that implicit context gets expanded by the implicit parameters. Okay, we've seen that we have implicit parameters. Well, a method can receive an actual, can have a formal implicit parameter. That means that when the method is called, it can get the actual parameter from the implicit context. But Scala is great because it allows, it makes that implicit value within the method body, it becomes an implicit value too. And that's cool. It's like a way of making a propagation of the implicitness. Okay, so let's see an example, and you will see. It will be easier to understand. We have the function, the method g, which receives an implicit parameter x of type int, returning int. That we don't care about the return type this time. Okay, and it multiplies the parameter by 2. If we call g with a value, it will, for example, with 3, G3, we'll get 6. If we call it with anything at all, we just write G, and in the implicit context has an implicit type, an implicit value of type integer, it will use it, as we've seen before. Okay, but there is a new situation. What is the condition, the tag of x within the body of G? So we have another function, f. F is exactly the same, okay? Receiving a value of type int and returning it. But it is calling g. As you can see, the call of g, it's without anything. There is nothing there. This should fail, okay? But since Scala has propagated the condition of the implicitness of the parameter, okay, this x becomes as an implicit value within its body. So you can call it without any parameter. It will propagate the implicit value. So the result here will be, it's easier, 6, okay? There are more complex examples, which is we have a case class C with an attribute x of type int, and then we have a function f. I really love this example because it goes beyond what you would expect from what we have seen before. You are receiving an implicit value called conversion, and it is of type function from int to C. And it's trying and it's returning a pair of two C's. If we didn't have this implicit parameter at all, this will fail. Okay, imagine you forget this line. This will fail because you are trying to assign an x of type int to a type C. That should fail. But because you have defined an implicit conversion there, it is not only trying to capture any function from its implicit context when f was called, but it is making that conversion implicit. And it will make the compiler to be able to perform the transformation from x to C. So you can do the following. You can call f with 1 and a function. So what we are doing here is that we are explicitly passing a function. It is not being resolved from the implicit context, but it is becoming implicit within the function body. And that's the main point behind this. So we'll be perfectly able to perform the transformation. There is more examples, there is not so much importance. It's important to keep in mind, however, that even though you have even though you have implicit, a parameter defined as implicit, you can pass a value to it. You can make it an explicit code. So let's visit another pocket. We have, another pocket, no, actually there are two pockets more. This is too long to pronounce, but it's easier than it sounds. Okay, so we have the implicit context gets expand by the target class companion object. Imagine that, okay? No, it's impossible to understand what the hell is that. No problem. We have seen before that the conversion has had two parts. The source, the source type, the source they are receiving, and the target type, the type they are providing. So the Scala does a little trick here, but let's see something. We have this assignation, okay? But we are trying to assign a value of type A to a reference to a value of type B. What do you think is the source and target type here? The source? The source is A, exactly? Exactly, easy. Piece of cake. Now, that's the same, but shifting the places, okay? We have changing the order, so changes the roles. Now, we have a function being called, a function expecting to receive an A being called with a B instance. What will be the source and target types here? The source will be B to A, exactly. So with this, and you might be thinking, okay, that's basic, okay, no problem with that. The thing is that both A and B are classes. In Scala, as you may know probably, classes have the possibility of have the companion object. And within the companion object, you can define an implicit conversion. So that companion object set of implicit conversion and implicit values get automatically inherited by your implicit context. And that's another way, another source of implicitness. And that's all, there are no more pockets here. There is no trick. Whenever you try, you find that you are getting implicit conversions or implicit value without knowing exactly where they come from. Go to 3 points. Go to your scope, go to the implicit context, go to the companion object, implicit definitions, nothing more complex, and go to your parameters, implicit parameters, but there isn't such a complex thing, there is no magic, okay? You have a piece of code where you find an implicit conversion, and you will see that there is no way of getting implicitness or implicit values from strange sites. You have just a list of four sites for looking for them. So this was like moving pieces in the chessboard. Now we can use this technology in order to create some patterns. We are going to see some of them. The first pattern is using the implicits as a way of propagating context. You see this guy is called Tux. This is a video game. I think it's called Super Tux. It's a clone of Super Mario. We have this enemy here. It's called Snowball, and some coins here, some items in the screen. If you were to develop this application, what do you think do Tux, the snowman, and the coins have in common? The same as you and you and you, everybody in this room have in common. A stage, a place, a universe to be. So if you're trying to create the software for this game, why will you continuously be making reference to your universe? There is no need to express in your calls. You have calculate next to the state, which will return your character state after some actions and iteration in your game. Why would you be continuously passing the universe to the functions? Okay, you want to calculate where Tux is and where will it be next. Where will it be in the next millisecond? You don't need to pass the state continually to it. Just have an implicit definition of the universe, and that's what this does. We have a run game frame, which is like the main body, with an implicit state, and whenever we have to use it, it gets resolved implicitly using implicit parameters. There is no difficult at all here. So why would you, on the other hand, not having implicit here will require you to write a stage here, repeat it continuously. It's just like trying to refer to when you're talking to a friend, it's like trying to be repeating his name continuously. It will be stupid, wouldn't it? And that's a pretty widespread application of the implicits for presenting context. This context, you will find a practical example with futures. You have a future, and you need a context for its execution, and you are not writing it continuously. You are passing it implicitly, the executor, okay? So, another example, another pattern here. Okay, this is a common problem in Scala. Forget about implicits. What do you think is going to return this pattern matching? We have a list of integers, and we are matching it against the type list string. Okay, so this should fail. Shouldn't it? I will say that this should fail. Well, the result of this expression is it's a list of strings. What? How is that even possible? This is ignoring the parameter. This is called type erasure, and this comes from the JVM. It's an imitation from the JVM. So you should have a way to propagate your types from compile time. That is here. This will compile, but it's providing an expected behavior, and you would like to be able to check types in runtime without any trouble and without having this kind of strange behavior. Well, you can use implicit for that, okay? If you, in your function where you're trying to perform that check of type in this level, you can define an implicit evidence of the type of the thing that your method is receiving, okay? We have L of type T, and implicitly we might receive the type tag. And what it will be providing is at runtime we'll have a tag, a representation of the type of T. Not only at compile time, but at runtime. So we can perform some checks of the type. Is the type of the value we have received of the type list of int? And in this time, it wouldn't be confused because type erasure gets absolutely overridden by the fact that we have runtime evidence of the type. And that's all, that's an application of implicits. And the cool thing here is that you don't need to tell the compiler to provide in your implicit context what the values for this are. The compiler will do that for you. So in this case, what is it of list of 1, 2, 3 will answer correctly. If you pass a list of strings, it will answer with the right answer too. And now it's time to see the last. Bear me for a few more slides. Now it's the interesting part, and it's what convinces me that the Scala here can be more close to Haskell than we think. We have a problem. We are creating a piece of software using domains from two other pieces, third-party software. Okay, so you are trying to integrate, and we are big data developers and engineers, so we should know that we should tackle with this kind of problem continuously, because variability is one of the features of big data. And we are trying to combine things from the world, from the universe of equipment, with things from the world of animals. You might be thinking, okay, for what? Okay, this is the software for managing farms. And we have equipment, cars, fences, tractors, and we have animals, cow, dogs, and we want to schedule tasks, such as fixing the car, improving the fence, fixing the tractor, or feeding the cat, feeding the unicorn, okay, feeding the dog. There are different actions in your domain, and your domain is the result of the combination of two other domains. And you are not the owner of the code containing the definition of requirements. You are not the owner of the code containing the definition of animals. There are third-party libraries they have provided you. So you want to integrate them, to treat them as they were the same items to be maintained in your farm. A classical solution is this. Where you have equipment from a third party, you can modify it, you can extend it. Equipment is yours, okay, no problem, and you want to work with animals in the same management system. Then the only thing you can do in Java and C++ is to create a wrapper. A wrapper is a piece of code with an attribute of the type of animal. So you already have an integration between the two domains. But this is kind of this presents many problems. You have maintenance problems, you have to be dealing with the interface of animal, which is a third-party software piece. You have to deal with many, many things. So what would be the solution, a cool solution for this? Okay, the guys who created Haskell in 1991, around that day, were smart guys. And they discovered that it is possible it would be better to classify not instance by classes, but instance of objects of one type, that is the type they receive at the definition time, and you can change that type ever, and then add a classification of types. And that classification of types contains the interfaces, the operations you can use with your with elements of those types. I don't know if that's very easy to understand, but the point is that instead of having, you imagine you create a dog. It is a value, an instance, an object of type dog. But that type dog is also of type of class dog. And you have already to define here the behavior, the operations. If you have a var method, you have to define it when you define the type. These guys imagine a way of splitting the behavior from the data definition. And that behavior can be added in a late phase. You don't have to add a definition time. So if someone provides you a third party with a software library with animals and equipment, you don't have the behavior there. They might provide you with some functions to work with it. They might provide you with some classification, with some operations to work with them, but you can expand that set of operations. And that's made with type classes. And that's an idea from Haskell. So you have this animal and this equipment. These are types. It's an algebraic type. You have an animal, which can be a cat, a cow, and unicorn. You have equipment, which can be a car, a fence, a tractor. But you don't have here the method meow, the method moo, the method, I don't know, whatever a unicorn does. Then you don't have the method, no? So this is the management of a farm. So methods here will be more like feed the car, feed the cow, feed animal will have a method, feed. And equipment will have a method, fix. And that's, those methods have in common that it's like a kind of maintenance. With Haskell, you don't have it. You have animals, which can be cats, cows, or unicorns. Equipment, which can be cars, fences, or tractors. And then, after these types have been defined, you add the behavior. You tell Haskell, okay, this type animal from now will be maintainable. And maintainable will have the implementation of those methods, fix, meow, whatever. Okay, in this case, maintainable will have maintain. An requirement that you do it with an operation. You can do it at any time. You don't have to wait for definition time for it. Just invoking an operation, you add that behavior to this type, and it's made in a delayed way. You can do it also, once you have done for animals, you can do the same operation with requirement. So you add, after definition time, behavior. That's the idea behind type classes. And Scala, with thanks to the magic of implicits, can be like this. So tomorrow you receive a library from BBA, and it contains the account customer information, and you can add to that customer new methods proper to big data, proper to data, proper to strategy, and you don't have to have their source. You can expand the behavior, and you can do it with some tricks using implicits. This is the definition for requirement. This is the traditional way of defining it in Scala, which is there is a trait, an interface, and you have case classes which are childs of that requirement. Okay, and then you define a behavior. That behavior is a set of operations, and it's easy. We know how to do that, and we do it with an interface. So a schedule maintenance, receiving something, we don't know what yet, receiving a worker, because the maintenance will be performed by a worker, and receiving a date in order to provide a scheduled activity. That's behavior, and we don't have the code for this. We can inherit from this. That's all private, and we want to add this behavior to that. It is possible. We create an implicit object with the name of the association. That isn't very important. But the point here is that you are making an association between maintainable and requirement. And you are providing a function from requirement, worker, and date to a scheduled activity using the services the management system provides to us. But this is the association to the behavior. And how this thing works, okay? The only thing you are providing here is a way of, you have an interface receiving things. In this case, you are making clear that that thing is requirement and receiving some context, and you provide operations with that information. So you have this object, you can import it, and just call a schedule maintenance, and it will add that behavior to requirement. But that thing of having to import it is like, okay, that's a trick, that's better than what we had before. But there is one thing, it is an implicit object. That means that if you have a function expecting a maintainable of requirement, the compiler will provide this behavior without having to import it. This isn't just a hack. This is not a silly example. We have already using this in Scala. You probably have already used it. This is something that I have shown before. We have a class, person, with a name, an age. We have an instance, people. And we need to order them. So we might go to the Scala standard library and use its quicksort. But quicksort, receiving the collection of people, doesn't know how to order them. What's the order? Why is a person before another person? by the name, by the int, we don't know. And you don't have the code of person, but you still can call quicksort. So you need a way of providing some behavior after the definition of a type. That's exactly what we did before with the form. Exactly, same mechanism. So what was maintenance is now ordering. That's the behavior, ordering. And we have an object of extending ordering. And adding the behavior we want to attach to the type. So now we can call quicksort, but we are not passing quicksort this object. It is just being passed by the compiler because it is an implicit object, an implicit value, and quicksort have an implicit formal parameter expecting to receive this kind of object. So we don't have to do anything. It's just like that. It's just like that operation of add the behavior, that plus equal, is this, nothing else. It is there. You don't have to do anything else. And then you can use it as we've been talking. Okay, this import is nothing related to it. This is a way of not having to write this is a way of showing that quicksort is receiving an implicit value. Okay, so we are implicitly. This is like another example. We have an implicitly ordering person. That's like asking the compiler to give it to you that behavior, and you're using just to compare two instances instead of using in quicksort. And that's a flavor of expanding functionality using implicit. There is another. It's a little bit more complex. Some people say that this is like the other one, that they are equivalent, and they are called magnets. And instead of relying on implicit parameters, they rely on implicit conversions. So it's the same case, same class, same behavior, but this time the behavior is defined here, was defined, it received the object over which it was about to perform the operation. This time, it doesn't do it. It just receives its context. And that's possible because the association operation is an implicit conversion from equipment to magnet. So in that implicit conversion, you add the behavior. And that's all. You just, whenever you want to execute, to run the functionality within maintainable, you just call it as you expect to do it. The compiler will apply the implicit conversion and you will be able to continue. It's very similar to what we've seen before, but using the other family of implicit things, which are implicit conversions. And that's, this is an example of use. So we create a method receiving a magnet. And instead, we have a car. Instead of applying the conversion, we just pass car to the method expecting a magnet, and the compiler will perform the conversion. I'm sorry for the length, but that's all. And I hope that this small time, I don't expect you to be able to use implicits at this level, no, but you know that they are able to provide you with this cool functionality which allows you not to copy and paste code, which allows you not to have to ask other guys to send their code, which allows you to expand different things without populating your domains, without populating code with strange Frankenstein monster parts, even and that's all. I hope that you stop thinking that implicits are a way of making code more hard, and they become a way of making your designs simpler. And if you have any question, feel free to come to ask right now, or maybe later, whatever. I'm there in Attica 4 across data site. So, Emilio?
Hello?
Yeah. Where?
What is exactly the difference
Between these two?
in one of the last examples, when you say implicitly, what's the difference when you doesn't use that word?
Yeah, implicitly means that you are not writing, for example, here, your type of this method is maintainable magnet, okay? The type you are passing to it is car. They don't fit. And you will solve that by importing this method and schedule maintenance and, by importing this conversion, which is this conversion, schedule maintenance, and using it here. It will be managed from element, schedule maintenance, C. But you are not doing that. The compiler is doing it for you. So you are not explicitly referring to the conversion. And that's the meaning of implicit.
I was referring to the previous example when you explicitly write implicitly.
Yeah, I understand. Yeah.
No?
No?
Later.
Here.
Continue. There.
This import.
Yeah.
Yeah. This.
What's the difference between the?
Yeah. This import.
Example.
Okay. Implicitly, you are solving that you are getting an ordering object for persons. Okay. That object, you have it implicitly, so you are resolving it. This implicitly is a function. Let me write it for you. I can show you right now. There it is, okay? Oops. It's okay?
Yeah.
Okay. I am writing it for you right now. Something similar. The only difference is that Scala provides this to you. This oops. I'm sorry. Don't laugh at me, but I can. That's all. That implicitly is a method receiving an implicit parameter x and returning it. So, whenever you call to it, you call to implicitly, I can...
Just to make explicit something that is...
Exactly, that's the idea. It's a kind of explicitator. Okay. That's the fine. You can call implicitly with 1, okay? It will return implicitly 1. Fine. And then we define an implicit vol. And you need the name. You can read the name and say it is an integer. And from now on, I have to give a name in the rebel. From now on, in your implicit context, there is a value available for implicitly to use. I'm sorry. Yeah. Okay, this is cool because as Scala already has defined that name, it is colliding. Okay, I'll change the name for you in order to avoid the collision. It's the same function. Let's call xt for cost data.
Example.
There you go, and then xt.
So you have to pass the type.
Sadly, yeah, you're right. Because the way of the compiler to know what does it have to capture, it's through the type. That's the key. Imagine it's a map of implicit things, of keys to implicit things. The key, that key is the value, is the type. You can write that, or you can do this. And then type inference system will take over and tell the compiler that you wanted an integer. And that's the role of implicit. There is a way of getting things from this back and telling it, okay, back, give me an integer in an explicit way. And that's great because if you are debugging your code and you are finding strange results, you can use it implicitly in order to ask the compiler to tell you what it is it using.
You ask explicitly for something
Implicit, yeah, that's it, yeah.
Okay, thank you.
Some other questions?
In the previous example, go back to the...
Try and. Where? Here?
Slowly. The previous one? Yes. You have the method schedule maintenance.
Yeah.
How do you call it this method? You can import and use this method in a class of the type car, or
You can do it, yeah. You can import it, or you can have, it's the very same example that here. You can import it, but you wouldn't be making any profit from using implicits, because you will be explicitly bringing the operation. Or you could create a function expecting a parameter of the maintainable interface. Let me write it for you, okay? You could do this. And there, I didn't want to talk about this, but you open your question is great for showing some cool things, okay? So now you have this method things, and then you parameterize it or no. Yes, let's parameterize it. And then you are an implicit. This is called behavior. Yeah, I'm fast, so it might not be right syntax. So, of type T. This is called implicit evidence. So within the method body, you will have that operation for free without writing the import. And that's the important thing here. The only thing you have to do is to refer to implicit evidence. You will write maintainable behavior dot and the operation. Or you could import maintainable behavior. And this very same line with a Scala, this is so common in a Scala that this parametric type can be omitted. I'm sorry, I made a mistake. I'll rewrite again. And instead of writing, I wrote badly the signature before is maintainable of T. Okay? This is the same thing than before, but this is so common in a Scala that you can remove this thing and write shortcut. You're telling Scala to write that parameter list for you. And you will find this everywhere. This is pretty common to find in ordering things. For example, and you will find one of the most common problems here. Okay, ordering. X of t. And this is, for example, a list. This is pretty common because you are providing within the do method body, you are not able to order things, and you are adding ordering behavior to something of type T, which could be whatever. It's not a subtype of ordered, it's not a subtype, and that can be also applied for numeric. You have another type class in Scala called numeric. And what it does allow to you is that you could write something like, it won't work because I haven't imported the things here, but it will be something like, you will be able to sum things. Otherwise, without implicit evidence, you will have a list of objects. And whenever you try to call the plus operator, the compiler will say to you, I don't know how to add up these things. I don't know if they are numbers or they are cats or dogs or whatever. But adding that implicit evidence, you are implicitly including the behavior for numeric. And that behavior is plus, minus, multiply. It provides you with instance of 0, 1, and that kind of things. And those are implicit classes, which is just a sample. You are adding behavior to a type. You don't. It's not that you don't have it. It's that you don't know the type. It's a generic type, but you are adding behavior over it. Everything we have talked today, it's checked at compile time. So if it compiles, it works. It's enough explanation for you, or are you dubious?
I now have a doubt with the
Micro.
So I don't get here. X is a list of whatever things.
Yeah.
You still don't know.
Yeah. This is as written. Let me rewrite it for you. This is a shortcut for this whatever. And then you are the implicit parameter list. Which is of type numeric of t. It's the same. So in the body, you have, if we had implementation here, you have an instance of implicit evidence. And that implicit evidence is the bundle, is the object containing all the operations.
But you need to have defined this implicit object numeric of type numeric T.
Yeah, the point is that Scala has a bag of ordering for doubles, for...
Yeah, but the question is the type of T is not included in this numeric...
No problem.
The case is contemplated by the numeric object, then you don't...
Cool, no problem with that, because you can add that behavior by yourself,
but
using the implicit context, but you have to provide it.
But you have to do it. Okay.
Yes, because it otherwise wouldn't know how to sum a dog and a cat. Yeah.
That was my question. How does it know how to
Yeah.
sum? And then a very silly question I had from before in the quick sort example. In the definition of the method quick sort, there is an implicit parameter, right?
It is.
Okay.
You are not seeing it because it is implicit.
Yeah, okay.
Let me show you. No, I'm sorry. There you are. It is here. Is an invisible parameter, actual parameter, which is being captured that way. The very same way than the example I was writing in the console.
Thank you.
You're welcome. Any more questions? That's all? Okay. So thank you for your time. It has been a quite long talk, and thank you for being here.